Hello, this is Dr. Armand bringing you another exciting pre-lab video uh, in Gen 1 Laboratories. In this lab video session, we'll be talking about the lab involving the spectrophotometric determination of food dyes. So we'll discuss a little bit about the procedural aspects of this lab. So sit back and relax and enjoy the show. So in this lab, we'll be using a 5 milliliter graduated pipette. 5 milliliter graduated pipettes are in increments of 0.1. We'll be using a 10 milliliter volumetric flask. We'll have some DI water. We'll have a stock solution of known concentration. You'll be using a red dye or a yellow dye. And we're going to measure out approximately 35 milliliters of the stock solution. So our stock solution, we'll say it has a concentration of 320 times 10 to the negative 6 molar. So we're going to measure out approximately 35 milliliters of the stock solution. And you can use a 50 milliliter graduated cylinder to measure out the solution. So we're going to pour some, as always, best practice, pour some in the beaker, and then measure it out and pour it into the appropriate glassware. So again, it's just an approximate 35 milliliters of your stock solution. And you'll either be assigned a red dye or a yellow dye. In this example, we're using a red dye. Then we're going to pour this stock solution into the 50 milliliter beaker, and the beaker is labeled stock solution so we don't get it confused. And what we're going to do next is we're going to rinse the pipette and volumetric flask with DI water and the stock solution. Recommended to do 2 rinsings with DI water and the stock solution, just to make sure that your glassware is clean. So when you're washing with the DI water, you just need about, well, with the pipette, you're going to suck up 5 milliliters of DI water by rolling the wheel down on the pipette bulb, and then discharging it by rolling the wheel up on the pipette bulb. And we want to do this twice. So you're going to do 5 milliliter of DI water to rinse the pipette. And we're going to do the same with the stock solution. We're going to rinse it twice with 5 milliliters of stock solution when we're rinsing the pipette as well. So when you move the wheel up on the pipette, it withdraws the solution. When you move the wheel down the pipette, it discharges the solution. Next, we're going to wash the volumetric flask. So when you're washing the volumetric flask, you only need to add about approximately 1 milliliter of solution to wash / rinse it. And we want to do this twice. So approximately 1 milliliter of the stock solution to rinse the volumetric flask, and likewise, it wasn't shown in the video, but it was also rinsed with 1 milliliter of DI water. And we're going to swirl it around, make sure we rinse it very well, and then we're going to put the top on it and flip it upside down 2 or 3 times to make sure we properly rinse the volumetric flask. And make sure you discharge this into the waste beaker as well. So for solution 1, we need 0.2 milliliters of solution. So let me explain to you how this works. So from here to here is 1 milliliter. So this mark here represents 0.5 milliliters. So what we want to do is we want to fill it up with liquid to 0.7 milliliters. And we want to discharge it back down to 0.5. And so this means a total of 0.2 milliliters has been added. So we want to fill it up to the 0.7 milliliter mark. We want to discharge it back down to the 0.5 milliliter mark. This tells us that 0.2 milliliters of solution have been added to the volumetric flask. And so this is what we're going to do to make sure that we get 0.2 milliliters into the volumetric flask. So now we're going to get that 0.2 milliliters. And we're going to add it to the volumetric flask, remembering that we're going to stop at the 0.5 millimeter mark. Now we have our 0.2 milliliters in the volumetric flask. We're going to fill the rest with DI water to the calibration mark. And so this is solution 1 again that we're preparing. 0.2 milliliters of stock solution. For solution 1. And make sure we don't go beyond the calibration mark. It's best to use a disposable pipette to add the DI water to the flask. This can be a very tedious process, but you need to be careful on this step. You want the meniscus of your solution to be at the calibration mark. So the bottom of the meniscus needs to touch the calibration mark. It may take a drop, a half a drop to reach that mark. And it's kind of neat if you go on your cell phone and zoom in, you get a very clear picture of the calibration mark and the meniscus. Then we're going to mix it a few times. So flip it up and down to make sure the water and the solution mix. And then you're going to pour it into a plastic cup labeled solution 1. And now solutions 1's prepared. We're going to begin preparing solution 2. So again, when preparing solution 2, we're going to rinse the volumetric flask out with approximately 1 milliliter of DI water. And we're going to do this after we make every solution so that there's no cross contamination. So solution 2 requires 0.5 milliliters of the stock solution. Make sure to put the washings into the waste beaker. So for solution 2, we required a half a milliliter of stock solution. This is to make solution 2. So there are 2 ways you can do this. I prefer one way over the other, but the first way is to measure the volume of liquid up to this line, which is the 0.5 milliliter mark. So measure the volume up to here, and then discharge it. That's 0.5 milliliters. So that's one way to do it. Another way to do it is to measure up to the number 4 and then discharge down to 0.5. So you discharge down to 0.5. This tells us that we have added 0.5 milliliters to the volumetric flask. So again, what you're going to do is you're going to bring up the solution, withdrawal solution up to the 4 mil mark. We're going to discharge back down to 0.5 mil. That means we've added 5 milliliters to the volumetric flask. And that's the method we're going to use to add 0.5 milliliters to the flask. So we've added the 0.5 milliliters of stock solution to prepare solution 2. Now we're going to add the DI water up to the calibration mark. And over time, you know, this is a little bit of a tedious process, but when you get to the calibration mark close to it, make sure you do it drop by drop so that you don't go over the mark. And again, when you get near the mark, you may need to go drop by drop or even drop by half a drop to make sure the bottom of the meniscus is it touches the calibration mark. Then we're going to mix it a few times to make sure that the solution and the stock solution and the water have properly mixed. And we're going to add this to a plastic cup labeled solution 2. So now we prepared solution 2 for our experiment. So we've already rinsed the volumetric flask with DI water and stock solution. Remember, we use approximately 1 milliliter of each to rinse it. So for solution 3, we need 1 milliliter of stock solution to make solution 3. So again, we're using a 5 milliliter graduated pipette. So what we're going to do here is we're going to fill solution up to this mark. And then we're going to discharge all of this out. When we do this, this is 1 milliliter of solution. So again, we're going to withdraw enough solution to reach this mark here where the 4 is. We're going to discharge it into volumetric flask so that we have 1 milliliter of solution in the flask. So now we're going to withdraw 1 milliliter of stock solution. So notice how the stock solution withdrawal up to the mark where it says 4, and we're going to discharge all of that into the volumetric flask. And then we're going to add the rest with DI water up to the calibration mark. When you get close to the calibration mark, make sure you do it drop by drop so that the meniscus, or excuse me, the meniscus of your solution, the bottom of it touches the calibration mark. As you can see, we're doing the same process over and over. We're rinsing, washing our glassware, adding the stock solution, adding the DI water to prepare our solutions. Then we're going to add this to a plastic cup labeled solution 3. Now we're getting ready to prepare solution 4. Solution 4 needs 1.5 milliliters of stock solution. So what we're going to do here, we're going to withdraw enough solution to this mark here so that when we discharge, we've added 1.50 milliliters of the stock solution. So we're going to withdraw up to this large hash mark between 4 and 3, and then discharge. We have our 1.5 milliliters of solution added. So again, we've already washed the flask, rinsed it. Now we're just adding the stock solution to it. So 2 rinses with DI water, 2 rinses with stock solution, approximately 1 milliliter of each. We've already done that. Now we're just going to add the 1.5 milliliters of stock solution to the volumetric flask. So it looks something like that. As you can see, it's halfway between the 4 and the 3 on the pipette. we're going to add this stock solution to 1.50 milliliters, and then fill the rest with DI water. So we're adding DI water to get to the calibration mark. As you get closer to the calibration mark, you want to do it slower, drop by drop, so that the bottom of the meniscus touches the calibration mark. And again, we're preparing solution 4. So solution 4 is 1.5 milliliters of the stock solution and the rest DI water. So again, you want that meniscus, the bottom of meniscus, to be right at the calibration mark. Put the top on it, mix it, and then we're going to transfer this to a plastic cup labeled solution 4. We're almost done. We got one more solution to prepare. Now we're ready to prepare solution 5. We've already rinsed the volumetric flask twice with DI water, twice with stock solution, using approximately 1 milliliter of each to do the washings. Now for solution number 5, we need 2 milliliters of the stock solution. So we're going to withdraw enough solution to reach the mark, the hash mark with, or the increment with 3 on it. That way, when we discharge all of this all the way to the bottom, we've discharged 2.00 milliliters. So again, we're going to withdraw up to the increment, the large increment with 3 next to it. Then we're going to discharge all the way down. We've added 2 milliliters of stock solution to the volumetric flask. And again, this is for solution 5. You got to be careful. Sometimes it'll drip out, so you want to make sure you're right at the mark. So here we're at 3 milliliters. You want to get the meniscus right at that increment. And we're going to add it to the volumetric flask. Again, we're preparing solution number 5. Then we're going to add DI water to the calibration mark. You want to make sure that the bottom of the meniscus is right at touches the calibration mark. Again, at this point, you want to go by drop so that you don't overshoot the mark. So even if you go over a little, you got to start over. So now the meniscus is right at the bottom of the calibration mark. We're going to put the top on it. We're going to mix it, and then we're going to pour it into a plastic cup labeled solution 5. So now we have solution 1 that was 0.2 milliliters, solution 2, 0.5 milliliters of stock solution, solution 3 was 1 milliliter of stock solution, solution 4, 1.5, and solution 5 was 2 milliliters of stock solution. So now we're ready to determine the absorbance of each of our dilute solutions. And what we should observe is as concentration goes down, absorbance should also decrease. So absorbance and concentration are directly related. So if concentration increases, absorbance increases. As concentration decreases, absorbance decreases. And you want to set your spectrometer to the correct lambda max. And so the lambda max for the red dye is 509 nanometers. Your TA will also have the lambda max for the yellow dye as well. And so what you want to make sure is that you press the button labeled nanometer with arrow up, nanometer with arrow down to set the wavelength to your correct lambda max if it's not already set to it. Now, lambda max is the wavelength of maximum absorbance for that particular compound or substance that you're using. Secondly, the second button is to blank your solution. So you want to remove any of the absorbance due to the solvent of the solution you're for making those solutions. So our solvent is water. So we want to have a blank of water so that we remove the absorbance due to the water from the measurement. And then lastly, the last button is the difference, I guess, items you can measure. You can measure the absorbance, transmittance, or concentration. For us, we want to make sure it's on absorbance. So first thing you want to do is you want to set the wavelength to the appropriate wavelength. And now we're going to add our blank and blank at this wavelength. So we're going to be using cuvettes. The cuvette has a triangle on it. That triangle should be in the path of light. So here there's a triangle. This triangle should be in the path of the light of the spectrometer. So you want to hold the cuvette on the sides that do not have the triangle. So perpendicular to the triangle are the sides you want to hold the cuvette on, because if you hold the cuvette where the path of the light goes through, that could cause some error in your absorbance measurement. So make sure that the side with the triangle at the top is in the plane or the path of the light. And so this is our cuvette, the blank, which contains water. So we're just going to put it in the cuvette, or excuse me, in the UV-Vis spectrometer. So here the path of light is this direction. So make sure the triangle is this way. You just put it in, you close the lid, gently close the lid, and then you hit the 0 ABS, 100% T. So it's setting the blank, it's removing all the absorbance due to the solvent. And the solvent again is water. Now we can start putting in our solutions and measuring the absorbance of each solution. So we're going to start with solution 1. We're going to use a pipette to add solution 1 to a cuvette. Now, please do not throw away these cuvettes. These are not disposable cuvettes. Rinse them out and put them back onto the cuvette holder. So again, make sure the triangle is in the path of the light. So solution 1 was the 0.2 milliliters of stock solution. It has an absorbance of 0.327. So you'll need to record the absorbance for each solution. So solution 1. And we do the same thing for solution 2. We add solution 2 to a cuvette. Now solution 2 had 0.5 milliliters of stock solution, so its absorbance should be greater than solution 1. Again, the triangle should be in the path of light on the cuvette so that the light passes through the clear side, not the frosty side. So it did increase, it's 0.430. Now we do the same thing for solution 3. So we're seeing the trend we're supposed to. As we have more stock solution, we get greater absorbance. So in solution 3, we had 1 milliliter of stock solution. You put it into the UV spectrometer and record the absorbance. So this is 0.541. We do the same thing with solution 4. So every time if you want to use the same cuvette, make sure you rinse it out with DI water and then rinse it out with a little bit of your solution. That's if you're going to use the same cuvette. Again, you should rinse it out with DI water and then rinse it out with a little bit of your solution. So solution 4 had 1.5 milliliters of DI water, or excuse me, stock solution. And our absorbance is 0.80. And then lastly, solution 5. as well. So solution 5, we use 2 milliliters of stock solution. And it has an absorbance of 1.097. So that's how we measure the absorbance of each one of our solutions of known concentration. And then lastly, you'll have an unknown. So for us, the unknown, we're going to measure next. So our unknown solution, we're going to measure the absorbance so that we can determine its concentration. So we put the unknown into the spectrometer and record its absorbance. So absorbance is 0.652. So now I'm going to show you how to do one calculation to measure the new concentration. And then we'll do the rest of them. We'll plot on Excel to show you how that graph should look. So to do the calculations for the concentrations, we'll do solution 1 over here. So for solution 1, we want to determine what C2 is. V2 is always going to be 10 milliliters. C1 is always going to be, in this case, your stock solution concentration, 320 times 10 to the negative 6. So just read whatever your stock solution concentration is. And V1 is 0.2 milliliters. So now we're going to solve for C2. We get C2 equals 320 times 10 to the negative 6 times 0.20 divided by 10. So we have so we get 1, 2, 3, 6. I did this correctly. 1, 2, 3, 4, 5, 6. So we got the concentration of solution 1 is 6.4 times 10 to the negative 6 molar. So now I'm going to switch gears and show you how to graph this data and to determine the concentration of the unknown. So here I've opened up Excel and I've put in the data. So here's the volume of the stock solution in milliliters. I've done the concentration. This is the concentration of the stock solution in molarity. So let me show you what I did here. So I've made a little equation. So $1, that's the stock solution, times A3, which is the volume of the stock solution, divided by 10, which is the volume of the dilute solution. And we've calculated the dilute solution concentration. So now what I'm going to do is I'm going to plot absorbance versus concentration. So we're going to insert a graph. Make sure you use XY scatter plot. No lines. We don't want to connect lines. And we want to make sure that the absorbance is on the y-axis, concentration on the x-axis, which is what it is. So now let me move this to another sheet. And so the chart title can be something like, you can put Beer's law plot of red dye at 509 nanometers. Something like this is a good title. Now on the y-axis is absorbance. Absorbance is unitless, so we'll just put absorbance. Well, let's try that again. And then on the x-axis is concentration in molarity. So that's labeling the axes. And the scale looks good. You want to make sure it's not skewed to one side, the scale. So now we're going to do linear regression, add trend line. We want to do a linear trend line, display equation on chart, display R squared value. And so again, the closer the R squared is to 1, the better your data fits a linear trend. So mine's a little bit off, 0.967. Now the slope equals epsilon b. B is the path length. Which is 1 centimeter. And E is the, or epsilon is the molar absorptivity of the compound. So different compounds have different molar absorptivities. So now that we know the slope, we can calculate the molar absorptivity of this compound. Also, we can calculate the unknown concentration. So the unknown, it was 0.652 equals 13083 times x, which is what we're looking for, plus 0.2036. So when we work this out, we get 3.4 times 10 to the negative fifth molar is the unknown. So now if we go back to the sheet, 3.4 times 10 to the negative fifth puts it between solutions 3 and 4. And so this would be the concentration of our unknown solution. So that's how we plot the data. We get the linear regression trend line. We can determine the molar absorptivity, and we can also calculate the concentration of our unknown solution. So that's how we use the data we acquired from the experiment. So that concludes this video session on the lab involving the spectrophotometric determination of dyes. We looked at the procedure involved with the lab. So there's a lot of rinsing. We're using graduated pipettes. We're using a UV vis spectrometer, which we have to blank with our solvents and set it to the, or first set it to the correct wavelength and then blank with our solvent. Once we get the absorbance data from our different solutions, we need to determine the concentration of each of those dilute solutions, perform a Beer's law plot, get a trend line, and from the trend line, we can determine the unknown concentration of our unknown solution. So on that note, that's all for this session. This is Dr. Armand signing off until next time. And again, if you like the chat, or excuse me, if you like the video or learn something new, please click the like button down below.